Yeah. So, oh yeah, thank you. All right, then let's start today's Origin seminar. So today, Shuo, maybe you can look at this camera. We have Dr. Shuo Kong. He received a PhD from University of Florida. His advisor was Jonathan Penn. And then he moved to Yale to work with Herschel, and then came to Stewart. We're very happy to have him here. So Shuo has a really wide interest in star formation, from ISM, molecular cloud, to the accretion. So from feedback from massive stars to the star formation, to ISM itself, initial condition of star formation. So all around in star formation wise. So I'm very happy to introduce him today. So Shuo, today the floor is yours.
Thank you, Serena. For those folks on Zoom, can you hear me?
Yep.
Okay. Yeah, so today I'm going to talk about our recent work on some study of molecular cloud formation in the Orion A. So the images here show the Herschel view and Y's view of the Orion A giant molecular cloud, and so you can clearly see there are many filamentary structure in the cloud, which you don't normally see when you look at, for example, near infrared or molecular, like low resolution molecular line data. And we know since Herschel that these filamentary structures are very important in star-forming clouds, because they're very common, and they are responsible for the majority of the dense cores that form stars. So studying these filament formation and evolution is, of course, very important. So typically there are several ways or mechanisms you can form filaments, like the turbulent shock in molecular clouds, or colliding flows, or gravitational instability, etc. But today I'm introducing a possibly new mechanism for filament formation. And all started with the Herschel data of the Orion A cloud, where we saw a pretty interesting filament in the L1641.
Sorry.
Right, in L1641 north region, which is in this region. And so we call this filament the stick filament, just based on its shape. And here I show a multi-panel infrared view of the filament from 70 micron to 850 micron. You can basically see this filament is pretty straight and with this long tail. So there are many filaments in this crowded region, but this one really stands out, and it just brought our interest. So we, based on the Herschel data and molecular line data, to estimate some of the features of this filament, and really the filament is starless, it's very young, it's very cold. So that's one. We really want to study how this filament forms and if there's anything interesting happening in this filament. So one thing we noticed was pretty interesting is in the C180120 molecular line data, when we combined the interferometer data from KARMA and single dish data from Nobayama. to get a relatively high resolution, high dynamic range image of the C18O. And in the channel maps, where it shows these molecular line emission as a function of the velocity, we noticed there's the two special channels where you see this more or less tiny, like fiber-like structure forming these ring or fork-like structure.
I'm sorry to interrupt. There was a question in the chat that asked, where is the boundary between the body and the tail?
In this one,
Mhm.
in this yeah. So this is the body, I think, and then the tail is to the lower left. Yeah, this one is the body. So in the C18O,
I don't think I can see your mouse on the screen.
Oh, okay, yeah. But the blue box here shows the body.
Okay.
And the tail is to the lower left. So only the body you're only able to see the body in the C18O map because the tail is too weak in the C18O map. But it's in this. You probably need to. There's a way.
Yeah, you can do
the annotation. Yeah. Or drawing, I guess.
Oh, yeah, drawing.
Yeah, so it's this feature I'm trying to highlight here. And yeah, so really it looks interesting, it looks funny, and we want to know how it forms. And this, we have a really simple motivation is this ring or fork-like structure looks like structures formed by magnetic reconnection in the many studies before. Basically, you have anti-direction or anti-parallel magnetic fields, and they, due to some instability, they will form these plasmoids with this looped field, and it will form this ring-like structure and filament-like structure. So really the motivation is just simple. The structure of that filament looks like the structure of generated magnetic reconnection. So we try to model that structure with magnetic reconnection. So in order to model that, we need to find the initial condition for the model. So the first thing we look at is the magnetic fields in the Orion complex. This is a famous map by Carl Hayles from 1990s, where he measured the Zeeman splitting of the, I think it's the H1 line in this large area of the Orion A complex. And so since then we have known that this Orion A complex has this flipped magnetic fields along the line of sight. So on the top, so Orion A is here, is this thing. It's basically this thing. Yeah. So above the Orion A, you see the field, a line of sight field direction to one direction, and then below the Orion A, you see the field direction to the other direction. So basically, the field direction inverted at the cloud, and so that's only the line of sight field. Recently with the Planck and Herschel, we also know from the polarization, we know the plane of the sky. So the source of the field can be many. It could be the large scale field inherited, or it could be just a dynamo from locally. So with this polarization map, we know the plane of the sky field direction.
I've got another question in the chat. What is the source of the magnetic field in these clouds, in these cold clouds?
Yeah. I just was saying the field can be, the origin of the field can be many sources. There could be inherited from the large scale, or it could be local dynamo effect, or it could be field from gas propagated with a supernova ejecta, etc. But this is the field we see right now. And then that origin, basically the origin of that flipped sign field is still like a mystery, I think. There are some models try to explain that, but there's definitely more work need to be done for that. But this is just, this is what we see. And with this polarization map, we know the field is the plane of the sky field. And this is the stick filament. So it has a large angle relative to the filament. But one thing to know is that this polarization map will only tell us the plane of the sky field line, not the field vector. So what it looks like is this is a very like a sketch, a cartoon is we have a filament here. We have a field line on one side is pointing toward us, and then the other side is pointing away from us. And then the plane of the sky field is perpendicular to the filament. So then with these idea, and also we know the density and temperature in this region. So the only possible way to use this cloud collision to explain this filament information in this region is this. And the reason we want to use the cloud collision is because we see double velocity components in the molecular line data. So basically you have this idea, you must have some cloud collision, and you have this field line configuration. You put all of these together, this is probably the only way you can have the initial, for the initial condition, where you have a clump on the left, and you have a clump on the right. They have like a different direction of the magnetic fields, and they are coming in with a collision velocity. And we, as the observer, are looking this way. So on one side, we have a field line point toward us. On the other side, we have a field point away from us. And then the plane of the sky field is perpendicular to the filament. So right now, the filament hasn't formed yet. It's just at this point, the filament has to form here. And we're looking at the filament cross-section. Only filament from this way can fit all the observational features we see from the data. So we just set up this initial condition, and we use the MHD code Athena++. And so here show the initial condition. You have to see the two spherical clumps. And we show the slice plots of the density, velocity, and line of sight magnetic fields. So with this public version, I was only able to use the uniform grid with self-gravity with periodic boundary conditions. These initial density, collision velocity, temperature, and magnetic fields, those all come from the observations. So we just want to see, we let these two clouds collide and see if we can form a filament in the middle. And yes, you just let it evolve. It does form a filament, which I show here. On the left, I show the three slice plots from the x equals 0 plane, y equals 0 plane, and z equals 0 plane. So especially I want to mention this panel where we are looking from the side of the collision. If I use annotation, we're actually looking from this direction. If you see my drawing there. So if you imagine, normally if you think two spheres collide together, it should form a sort of a compression circle or compression pancake, I call it. But here in the middle panel, you see there's a filament forming in the middle of this sort of pancake instead of a compression pancake. And on the right, you probably already see there's a filament formed instead of a dense compression plane. And the third panel on the lower left, we're looking at the filament cross section, where the filament is forming in the middle here. So so then with this initial condition, we do, and with this magnetic field setup, we do form filaments like the way we want it from the observation. And here I show a little movie for the 3D volume rendering of the filament formed in the middle. So we're rotating this filament, and then we're showing it at different time steps. And you can sort of see the filament structure in you have the 3D idea of this filament structure. And you can see in the middle, there's dense core or dense gas formed in this center of the filament. And this filament shows this weird, like wiggling structure. Okay. So here I show some magnetic field streamlines in this 3D, and you can see the filament forms in the middle with this more or less helical field lines surrounding the filament. Here, just to show in a different projection. Hope you can see. Where's my mouse? And I hope you can see this some helical field surrounding the filament in the middle. And so this is what happens with the field lines and density in this model. So below, I will first try to compare with the observation, and then I will so I see the question from Neil. We don't really know what was the initial condition for the colliding clouds. It might be a spherical clump, or it might be like with other shapes. So right now we just really simplify it as two spherical clumps, and it can form the filament, and that's good. Of course, you can later do parameter exploration, see how different shapes will trigger the filament formation. I hope that answers your question. Below I will first show the observational features and see how this model can match the observation, and then I'll introduce the physical explanation of this. First, an interesting feature is I compare this fiducial model with a model with parallel B field, no anti-parallel B field, so no magnetic reconnection happening here, and another model with no magnetic fields. So without magnetic fields, it's easier to understand. You can see there's just a circle in the middle due to the collision compression. And you see this two halves is because there's a little shear velocity. So when you make the slice plots, like top half is showing the dense gas, the other half doesn't show. And then in the middle is the collision with the normal, like parallel B field. There's many studies about this. And here, due to the magnetic pressure, it's not easy to form a structure in the middle. But anyway, it doesn't form a filament in the center. So it seems is this really this filament formation is due to these anti-parallel magnetic fields in the setup. So to compare with the observation, we need to choose a correct time step. Here we just choose the filament at t equals 0.6 million years. Simply it's because we have done some test, and this one probably matches the observation best. And here you can see this filament shows some pretty weird structures with this little ring or fork-like structure, fork at the side, ring in the middle. And on the right is the fork and some spikes in the middle. And this is another projection, basically. If we compare that with the observation, first is we compare with the integrated intensity map. This is just one CNC. Notice that you have some spikes in the side of the filament. That just looks like that, but that's just one thing. The other thing is, previously you already see the C18O map. Here, just I want to show the 13CO map. 13CO map is optically thick in the body part, but you can see at the tail, there's this fork-like structure on the lower left. If I clear, I'll just change the color scale. You can see it probably more easily. This is just a more like shape morphology comparison, and then we do a radiative transfer modeling for the model, and we make the synthetic observation for C18O molecular line data cube, and there you can see the like ring structure, fork structure in the channel maps of the C18O map. So this is just another comparison for the morphology. And we also compare the probability distribution function for the 850 micron flux density and also the column density with Herschel. So basically they match for the high density region, for lower density region, because we didn't include other like lower other structures. We're just focusing on the filament. They match pretty well, but if you want to have a very good match, you can increase the initial clump density by a small factor, and the density PDF matches better. And also we compare with the sort of the position velocity diagram. So here, I show the filament, and we pick these circles to make a position velocity diagram across the filament. So just to see the kinematics change around the filament. So for the observation, from C18O, it looks like this. You see the double velocity. So on the x-axis is the velocity, on the y-axis is the offset from the filament. And so basically you see two velocity components. This is why I was initially saying we need a cloud collision to make this happen, because we see these two velocity components. And these two velocity components cannot be explained by global collapse. We have also modeled that. A global collapse will show much higher velocity at the filament. But here it's not. It's just the two velocity separated by about 1 or 2 kilometers per second. And here the filament is at offset of 100. So this is a C18O. We also see this two velocity components in independent measurement, which is from the gas survey by Friesen et al. They used ammonia to trace the dense gas. Because it's tracing denser gas, you only see probably the most central part of the filament. But you can still sort of get the idea of these two velocity components in this diagram. The different panels are just the different locations I picked along the filament. So, and this is the model position velocity diagram for the C18O synthetic observation. You see the two velocity components, and you see the dense filament in the middle. So I would say this is a reasonable match, but the filament shows probably some a rotation in the middle. It's probably also because we includes the shear velocity, but basically it reproduced the double velocity component and the filament in the center. So we would say that this model matches the observation in many aspects in the magnetic field's direction and polarization, kinematics, density, also morphology, etc. So now I just go to explain the physical origin of this filament formation, why it forms filament. So if you just zoom into the slice plot and then put the magnetic field streamlines on top of it, you can notice that at this two place, you see the field line sort of merges together. And that's where the magnetic reconnection happens. And once the magnetic reconnection happens, it will form a loop field in the center. You probably see here, and it will form half loops there and then half loops there. And because these loops are very has this sharp turn, and this sharp turn will have a magnetic pinching force on the gas, which is coming from this term in the momentum equation. And it's that force is pulling the gas to the central filament, the central axis to form the filament. And it's pulling away the gas from the two sides. If I just skip to the next slide. Okay, well, before I go to the next slide, here you can see on the right panel, I show, so the filament should form here. And on the positive Z axis, you see so the color shows the velocity in this plane. The positive Z, you have the negative velocity, and the negative Z, you have the positive velocity. So gas is being pulled into the center axis and it's formed accumulated dense gas to form the filament. So here I show 4 slice plots for the different terms in that momentum equation. So the filament is here. We're seeing the cross section of the filament here. So the filament is really pointing into the screen. And here I show the Z axis on the left and the axis is in the horizontal direction. And the color shows the Z direction force. The top left shows the tension, magnetic tension force, and you can see they have the negative force here. So these forces have negative Z direction. They're pulling the gas to the central axis. And the other forces are not dominating. We only see them accumulating in the center of the filament. So that's sort of the way to show how this filament is accumulating the gas. And so what causes this magnetic reconnection? One interesting thing is if we don't have any structure, like a spherical clump in the collision, you just have the two sides of uniform density collide each other, you will not form this reconnection, not trigger the reconnection. It will just accumulate high density gas in the center, but not very high density. So somehow it's the shape of the clouds is triggering this formation. So if you look closely, I zoom into the simulation slides. You can see the two clumps colliding from the two sides. On the left panel is the initial condition, and then the middle panel is shortly after the collision. You can see there's ejection of some gas here. It's being ejected away from the center, and also same thing happens in the bottom. This thing is being ejected away. So between the ejection and the high density region, there's a low density region, lower pressure. And because we continue to have collision gas coming from two sides, you actually forms an X shape of the field line in this region. And this X shape is pretty well known for magnetic reconnection in this Sweet-Parker model that we have known for a while. Basically, I think a lot of the solar science use this to study the magnetic reconnection in the sun, where you have the incoming gas pushing the magnetic fields, and you have reconnection here, and then the reconnected field on the two sides goes away. And because we have also the reconnected field in the center of our film, of our cloud collision, it has this looped field that pull gas to the center that forms the filament. So to test the resolution effect, we go to so Neil, the unit, sorry, I was using the code unit, but basically the code unit is 2 million years. So point 1 is 0.2 million years. 0.01 is 0.02 million years. So here's more like 0.03 million years, something. So basically you go to higher resolution, this thing continues to happen, and it is easier to happen actually. You see many smaller, tiny, like magnetic plasmoids formed in the center, and you see the loop field on the right panel. And an interesting fact is that if you actually go to a higher resolution, the reconnection happens easier, and the reconnection, like the resulting gas, becomes denser. So I think, so then in reality, if you just, I don't know, like if you go to a really high resolution simulation, maybe you can form very dense gas. So that's another thing to explore. So with these knowledge, it's interesting to compare again with another, So we apply to analyze the another observational feature, which is there was another study by the Kirk et al. From the gas survey where they studied these dense cores in Orion A. They found the majority of these dense cores are pressure confined. Their gravity is not able to dominate the support of these cores. So basically, these cores are not gravitationally dominated. But why do these cores exist? Their conclusion was that probably because of the cloud weight is acting on these cores. So, these cores has an environment with many like gas as the giant molecular cloud, and they are confining these cores. But if we explain this filament by this collision-induced magnetic reconnection, these cores are actually confined by the surface magnetic pressure, because we know there's this loop magnetic fields formed around the core, and they're basically parallel to the surface of this core. So now if you look at the Vero theorem, this surface term of the magnetic tension dominates I actually calculated the contribution of different of these terms. And then actually this magnetic surface pressure, or surface term of the virial theory dominates. So these magnetic pressures is confining this cores. So what will happen later is probably when this cores cool down a little bit more and more gases infalling from the surroundings. So the core becomes denser, colder, and heavier. It will eventually collapse and form stars. But at this point, with the Athena, we're not able to answer this question yet. We're only able to model the formation of the dense filament. So a summary here for the Athena result is we're basically trying to model this interesting filament called Stick. And it's very young, it's excellent target for a study of the initial condition or filament formation, initial condition for star formation. This filament shows some interesting structure in the velocity channel maps and also in the Herschel maps. And with a simple motivation, we basically try to explain the formation of this filament with a collision-induced magnetic reconnection scenario. And then we applied the synthetic observation for the model, and we were able to reproduce many of the observational features based on the previous data. And then these cores in this filament will be confined by surface pressure. So with this mechanism, you will naturally have a helical field around a filament, a dense filament in the interstellar medium. So this goes back to the interesting question that somebody raised during the talk is, we have long known this Orion A cloud has this flipped magnetic field on the sides. There has been models trying to basically say there's helical magnetic fields around the yeah. So in the so in this model initially I didn't include any turbulence. So that's definitely a direction to explore. One interesting aspect is if you include turbulence, you will pretty easily trigger the magnetic reconnection. So how that affects the result is unknown now. But back to the Orion A, so there's models trying to say Orion A is wrapped by a helical field around this main filament. Well, if Orion A, if we have two clumps collide each other and you with this anti-parallel field, you will naturally have this helical field wrapping around the filament. This is the natural result. So a wild guess here is because we see from the Zeeman effect, right? The Orion A has this flipped B field on the line of sight, and then perpendicular field based on the polarization map. Maybe the Orion A is also triggered by this collision mechanism. So Orion A has been, there's many supernova, there has been some supernova event around Orion A, some clouds might collide, but that's an open question, I don't know. We're right now just focusing on this information of the filament. So as I said, one of the question is, will this filament form stars? So with the Athena model, we were only able to form the dense cores in the filament. So to further study the star formation, can star forms happening in this filament, we use another code called a REPL, which is a moving mesh code with really good resolution. And it has the ability to, with the heating, cooling, and sync formation, and also with the chemistry, cosmic ray, etc. So we're trying to trace the sort of the realistic process of this mechanism. So here I show again the slice plots. These are some preliminary results. And here I show the slice plot for the cloud collision. This is in the XY plane. And in the top left panel, you see the initial condition. You have two clumps again. And they collide and they form the central filament. And starting at about t equals 0.64, a sink forms in the middle of the cloud. And an interesting thing is that actually this filament, if you look at here, starts to collapse along the filament to the center. And that's when the sink forms, because it has an overdense region in the middle with high density, low temperature, and converging flows. And the white dot here shows the sink in the middle, and its size is proportional to its mass. For this specific model, the initial sink formation, it was 0.04 solar mass. And at the end, the sink grows to about 1.2 solar mass in the middle.
I have a question. Is it just a forming single star only?
Yeah, it's just a one sink. Single star, right? Yeah. But we have for this formation criteria, we have a very strict or careful criteria where we check a very large volume, like a 0.5 parsec volume. So if within this volume the gravity dominates, it will form a sink. But really, the center region has very low density, high density, low temperature. Its Jeans radius is much smaller than this. It's probably 0.05 parsecs. So really, we should form the sink with that radius. And if you use that small radius to form the sink, it will form many more stars because it has a more dense gas along the filament. So I'll try that next, but then with that, I expect you can form a little cluster maybe, and then the filament collapse at the same time. It forms many sinks, and they will collapse to the center, maybe from a small cluster. I don't know yet. Yeah, but that's a very, very good question. This is again another slice where I show again the cross section of the filament with the magnetic field streamline. And again, you can see something you have seen in the Athena simulation where we formed these loop field in the center. That's where the dense filament is forming. We're seeing the cross section of the filament. And the field reversal plane is here. So basically, this is just saying first, the REPL result confirms the Athena result, where you do form this dense filament in this collision-induced magnetic mechanism with these this field configuration, and it does form star. It forms a sink in the middle, and so the conclusion is it will likely form a star because when the sink forms in the center, it has high density, low temperature, and the converging flow. By converging flow, I mean is here. So here I show another slice, which is the x equals 0 slice, and I overlaid the velocity vectors here, and the background color is the density. So initially, you can see the collision happens and you form sort of this pancake here, compression pancake. So we're looking at and this is a collision, we're looking this way. And this is the central slice. And you see there's some velocity vectors pointing to the central axis, and that's because the field line's pulling things in the middle. And later, maybe these arrows are a little bit too small, and you see this dense gas start to accumulate to the central region, and then eventually it forms the filament here. So at the t equals 0.5, which is 1 million years, the filament is pretty obvious here. And it's just a dense filament. But starting like beyond 1 million year, you can see there's a larger region starts to collapse. That's because the gravity of this central dense filament starts to dominate. And you can actually see some little vectors here on the side of the filament start to point to the center of the filament. So the filament is collapsing. And the filament collapses to the center and forms later more like a dense core in the middle. But then at this time, go ahead.
Yeah, there's a question from Ravi. So have you applied this model to filament structures to other clouds to check it?
No, that's a good question because for other clouds, we don't have like a very good data for magnetic fields. You don't really know if other clouds have this magnetic fields at the different direction. I mean, you can always try to model it with a collision and probably match the morphology, the shape. But I think at this time, a key step is to see with high resolution, high sensitivity Zeeman measurement along different filaments to see if it has like different magnetic field direction on the two sides. One thing you can also try, which is something we're working on, is we simulate many of these filaments with different initial conditions. So we have a bunch of filaments with different shapes or morphology and structure. So we, with an undergraduate student, Abichel, we are using the machine learning to train the machine learning for all of these filament structures. And then we go to the observation to find candidates that really match some structure somehow picked up by the machine learning. And then with those, probably we'll next observe Zeeman like effect around the filament to see if that's a good candidate. So that's one way to go. UV radiation environment, to what extent is it? Nice. Oh yeah. Yeah, we didn't measure the UV field around. It's just we would say the stick filament is well shielded because its temperature based on Herschel is as low as 15 Kelvin. So here, the REPO code model, we actually included an UV field, which is just the drain field. So the UV field is radiating from every direction to the computational domain. And the code has the self-shielding base for dust, hydrogen, CO, etc. So it self-consistently calculates a column density at different directions. So it will have this real sort of more relatively realistic interaction between the UV field and the column density. And here the filament forms, and the filament has about 15 Kelvin temperature in this model. So it must be like well shielded from the UV field externally. Yeah, but here the model is only one drain field. We don't know the radiation in that stick in the Orion A at this point. Maybe Hyperion will help us to measure that. Yeah. So back to this again. So at later time, you can see the filament collapses and form in a more or less a dense core in the middle. It becomes a spherical shape, and with this interesting X-shaped structure around it. And this X-shaped structure, at this point, I see it's because of the collapse from two sides, from the left and right, and top and bottom. And this X-shape is where these collapsing gases meet, and it forms like a overdense region. And at beyond the 2 million years, you just see this dense core in the middle. And with this like a sort of a global collapse, all the velocity vectors are pointing toward the core. So it's everywhere gas is being accreted by the core. And the white dot again shows the sink mass. So another interesting thing here is this core mass grows as the sink mass grows. So from the sink mass formation here, its mass continues to grow by accretion. At the same time, the core is also accreting mass from like everywhere. You can see it from the simulation. So this is another interesting result that Yancy and I was looking at in another cloud, where we speculate that these protostellar cores, where they already have these like protostar accreting, launching outflows, those core masses are also growing. So it has this more or less a dynamic picture where the core accretion, like this core in the sense around the protostar, the core is accreting, and then also the central star is also accreting. So it's like happening together at the same time. It's not like you start with a virialized core and sits there for a while and then collapse and then form stars. More like a dynamic picture. Yeah. So, but anyway, with this model, just the preliminary results, we're just trying to say it can form stars. And this answers the earlier question. So this is just another interesting thing is when I was talking about that interesting X-shaped structure, I remember a couple of years ago, we were using the Arizona SMT telescope to map the California cloud. We also saw interesting like X-shaped molecular gas in the California cloud. And that was a paper led by Nia Imara. So I don't know if that's a coincidence or maybe we can further study that. That's an interesting coincidence, maybe. So, okay, so yeah, just now finally come to my conclusion is though, with this mechanism, we can form the filament and the filament will collapse, it will form a sink, so likely will form a star. And then later it has a global collapse to form a dense core. At the same time, the protostar inside the dense core will also accrete to grow in mass. So the core mass and the sink mass grow together from this dynamic picture. So we're just trying to say the stick filaments can be explained by this mechanism and it can form stars in the future. There are probably many other interesting features to explore in next. And thank you for your attention.
Okay, so can you raise a hand, or you can actually speak up to ask question, and can show your turn on your videos when you ask question. That would be great. Okay, so while waiting for hands to raise up, there are a couple of okay. So there was a question. I think you answered most of the questions. Yeah, Tom Howard asked about the UV to see up to what level of turbulence in the initial cloud. You answered about turbulence.
Yeah.
And then I think, yeah.
Here.
So John Faydong asks, I have a theoretical study published in this link that investigate the role of reconnection plasma MHD turbulence. You may view the small fraction of the computational domain is your whole domain. So you did several tests on the grid resolution, but in order to correctly capture reconnection and plasmoids, you need to resolve certain layer width that is related to magnetic Reynolds number. Otherwise, the reconnection in your study is purely numerical. Does your conclusion depend on your grid resolution?
Yeah. So that's a very good question, and I have spent a lot of time thinking about that. As the conclusion of the filament formation, if your resolution is very low, you can still form a filament, but not very dense. Until if you have a very, very low very, very low resolution, the filament is not very obvious. You really, you don't only see the filament. And then I was showing in one slide where if you go to higher resolution, the formation it becomes easier and easier. Yes, so that's related to the magnetic Reynolds number, which is basically the length scale times the velocity divided by the resistivity. So there you actually introduce a scale, which is below that scale you will have a small Reynolds number, and then the magnetic diffusion becomes important compared to the dynamo. And also, what I would say the conclusion is you will form, after you reach a certain level of resolution, this filament formation will always happen. And in the Athena simulation, it's not purely numerical resistivity. Athena actually has a explicit resistivity in the code, where you can actually play with it. Using increase or decrease the resistivity, you will see some difference there. With the repo simulation, you only have the numerical resistivity. So we're not able to control the resistivity like explicitly. But based on all the exploration now, the conclusion is the filament will form after after you reach a certain level of numerical, like the grid numerical resolution.
Yeah, I want to ask this is Chuanfei Dong from Princeton University. So I want to ask, when you study the star formation, so if you use high resolution, then there will be multiple plasmoids, for example. If you use low resolution, then there will be only one. I think someone also asked how many stars can form. I feel that seems depend on your grid resolution. If your grid resolution is very high, it seems it can form multiple stars.
Yeah. So that's possible. But one thing here is you will form the dense filament at the collision point will have an advantage because it has you have the clump, which is denser than the environment gas. So there you will accumulate more mass in this the collision point between the two clumps. And of course, along the field reversal plane, there will be other plasmoids, right? You will form other dense filaments there, which you more or less see in this slide. I need to try to find a slide where this is the Athena result. Yeah, if you look at the slides here, actually, this middle plane is the reversal plane, and then on top and bottom you also have the plasmoids, and then there's dense gas. Well, they don't form the filament. They will form those dense wiggles there. But I'm also new to this. I'm not also new to this magnetic reconnection game, but I just think this dense gas provided by these dense clumps gives this dense filament some sort of advantage. So it can build up a dense filament in this middle that dominates over other regions. Now, this other environment has very low density.
Even in the middle, your green region, there should be multiple plasmoids because, in reality, we know those molecular clouds has very large magnetic Reynolds number. And once those plasmoids form, they will eject from the center. I feel, based on what you say, you think there will be only one plasmoid in the middle dense region. Yeah, that's your picture. I think you have some 2D simulation. You
here.
also see a lot of plasmoids. Not this one.
This one.
I think not this one. You have some 2D study. Maybe this one. Yeah, maybe this one. So but you know, if your resolution is high enough, I can guarantee you will get more plasmoids in the middle.
Yeah. So here you actually see multiple plasmoids there, right? So there are things, but well, we can make a test. I haven't tested that, and I honestly don't know the answer. But at least here, you will form multiple dense gas, but they are being, because you form more like field loops around it. They will continue to, so this sort of like a big loop is continue to push whatever dense gas you form to the central axis. So from the center, like maybe it's a multiple plasmoids or multiple filaments merge into the central filament. But I don't know, you know, if you go to super high resolution, will they just maintain multiple parallel filaments in this collision midplane or not?
You know, you can click on my paper later. You will see how they look like if you have high resolution simulation.
Yeah, sure. So we can definitely talk further. I would like to, you know, discuss more about this. The other thing is, there are several like these interesting features that we clearly see in the observation. And, you know, we always go back to the observation, and the observation, there's only this one filament. Like, so that's a little bit assuring that, well, I don't know, I'm just speculating. We can just discuss more later. Yeah.
Sure. Yeah, thank you.
There's one more question near Turner. Does the cloud's plasma satisfy the conditions for the reconnection to follow the Sweet-Parker model? And how well do you especially resolve the current sheet given the expected magnetic diffusivity?
I would just say the Reynolds number, magnetic Reynolds number in this 512 grid simulation was somewhere around 40. But there's no way, we don't really know the ionization fraction or anything around this filament, molecular gas. You know, when I try to model this, put together these pieces of the model, we're only able to consider the velocity, the shape, the density, etc. So of course, we can further test this model with other observations. But right now, I don't have that number.
Okay, so I have a last question. So can you go all the way to the first slide?
Mm-hmm.
So that shows our observations, and that actually shows three different UV environment on top. That's NDC 1977. In the top circle, the bright area. Yeah, that is intermediate kind of UV of what Tom and I call it, about 3,000 times UV radiation field around the solar system. And then you see the most brightest part, the most dense one in the filament, that's the Orion Nebula cluster.
This one?
No, the densest part, yeah, that one, that area. And then when you go all the way down, the helical structure filaments have been seen in that's in 1641.
Oh, yeah.
Yeah, all these areas, that's a very low mass. There is no high mass stars.
Yeah.
Around the ONC, just below there are pretty quite a number of OB stars. But then the bottom, you can see that if you, the third image, the black one, it's a less nebulous area. That is very low UV. So we do have some information about UV background, but the helical structures is seen very well in 1641, while you can see very complex structures on top where clusters have formed. So those are about 1 to 2 million year olds. So some of them may be up to 2.5 or 3, but they're all very young. So I'm actually very curious when you form multiple clustering stars, how they will connect to the observed stars. So that's
Just need to try to run different models. There's one we just simply don't know exactly what's the initial condition. Like initially, what's the colliding clump's mass, etc.
Okay, we can chat in.
Yeah.
Okay, so thank you very much, Shuo, and then let's clap again for the rest of us who are still here.
Yeah, thank you.